recording the session as well, so I remember. Grand, okay, so we'll get going then. So good morning to everyone that's on the line. You're very welcome to this Sustainable Energy Communities training course, and we hope that you're all keeping safe and well. We're delighted to have you here with us for this training this morning anyway. You're all probably aware that we are running a series of webinars over the course of May, and some of you might have already joined some of the sessions that took place last week, or you might be signed up for a few more this week or next week. But overall, the response that we've been getting to the webinars in terms of registrations has been great, so it's really good to see that interest there. The subject for the course today is renewable heat, so it's one of 10 courses that we're currently making available, and this is the second session of this particular webinar. And all of the courses that we are running are intended to be foundation level courses. So it's really to provide an introduction to you on the various different subject areas and how they relate to sustainable energy communities and what the general themes mean and how communities have been putting them into practice. So I'm your SEAI host for today, and for those of you that don't know me, my name is Caoimhe McCarthy, and I am part of the Sustainable Energy Communities team within SEAI, and we also have some extra support on the line today from Sarah McGinley, who is an intern with us in SEAI and is supporting the SEC team. Your trainer for today is Stevie Donnelly from IT Sligo, and we also have Mel Gavin on the line as well from IT Sligo, who will speak to you a little later on. Before I hand you over to Stevie, it was just to give you a quick run through of the plan for the course today. So we expect that there's around 30 or so attendees that were registered for this session. There's around half or so of you online now, so we might get a few more joining in the next few minutes. The presentation is going to be recorded as well so that we can share it beyond the group at a later date. We likely won't have them publicly available on our website or our YouTube channel or anything like that, but we will probably make them available through the mentors as well, or you can email the SEC mailbox if you would like a copy of that video. So the proposed approach is to automatically put everyone's microphone onto mute, if that's all right, obviously apart from Stevie. And also, if anyone does have their camera switched on, could you please just make sure that they're switched off for the time being, just so that there's no accidental interruptions or any background noise during the session. And it'll also help to keep the quality of the connection at its best throughout the webinar as well. We do welcome your questions as well during and after the presentation, and the best way for you to ask your questions as we go through is just to pop them into the chat box on Microsoft Teams, and I'll keep an eye on any questions that are coming in as we go through, and then we can discuss them with Stevie and Mel at the end of the presentation. And if we don't get a chance to answer all your questions, we're sorry, we will probably get a chance to get to as many of them as possible in the time that we have available. And if there's anything you'd like to follow up with us on after, you can just send us an email at our SEC mailbox and we'll follow up with you then. So the webinar is expected to last for about an hour. The presentation will take about 40 minutes or so. And then the rest of the time is just to cover, obviously, this introduction and then any questions and answers at the end. And we'll email everyone a copy of the presentation slides after the event, along with any other information that might be of use to you. We're also going to send you a very short survey in that email as well. So we'd really appreciate your feedback. Even if you just answer one or two of the questions, it'll really help us a lot, because obviously we don't know when we can all meet next face to face. So it's really the best time now to be getting the format of these right if we do any more training online down the line as well. And then if you have any other feedback for us, just in terms of the SEC program more generally, there's a feedback box at the end of the form as well on the survey where you can capture any other comments that you might have for us. And at the moment, each of the webinars is running twice during May, and then if there is interest in running more, we can look to do that in the coming months as well. So I think that's pretty much it from me. I'll pass you over to Stevie now to get us started, and just to say thanks again to everyone for taking the time to join, and we hope that you enjoy the webinar.
Okay, thanks very much, Caoimhe. I hope everyone can hear me and see the screen. So I'll kick off on the presentation. Thanks again for joining. So today we're going to talk about renewable heat. Apologies, the date there is the 8th of May because we ran this course last week, but it's the same course again for those of you who weren't able to join that day. So why are SEAI running these courses? So as part of the SEC program, you can join the SEC network, and then as you develop your SEC, you might apply for some Energy Master Plan funding from SEAI. And in order to do so, you have to tick a few boxes. And one of them is to look at the competency development. So SEAI have identified 7 core competencies, and these are basically the skills necessary for community energy projects to succeed. So you can see there on the right a little diagram of what those competencies are. And then on the left are just listed out. So we have number 1, energy champion, which is also called partnership and engagement, integrated planning and strategic financing. Then you have energy efficiency, renewable energy, sustainable transport, and smart energy, smart grid. So many groups might already have good experience with the first 3, integrated planning, partnerships and engagement, and strategic financing. If you're something like a community development organisation, you might already have good experience with that, with running other projects in your community. And so then the other competencies in blue are those that you'd like to bring into the group and get support from SEAI. So today we're talking about renewable energy, and renewable energy is such a wide field these days that we've decided to split it into 2 separate webinars. So the first one is renewable electricity, which covers solar, photovoltaic, wind, hydro, ocean energy, which includes wave and tidal, and then separately renewable heat, which is solar thermal, biomass, biogas, heat pumps. And I'm also going to talk a little bit about district heating today. And just to note that there will be another webinar on renewable electricity, I believe, next Wednesday. Confirm that at the end. But again, today we're going to talk about renewable heat. Okay. So just to give some examples of what renewable energy might look like in the community, here's just an image of a small village. So you could have some solar PV on your local shops or cafes, and it works well with 7-day businesses like petrol stations and whatnot. Then you could have some homes that have solar thermal panels on their roof to provide some of the domestic hot water demand. And I'm going to talk a bit more about that. Then you could have biomass boilers in your local B&B or hotel. You could also have a biogas plant in the local farm in your town, and that biogas plant could then provide heat to a district heating system, which is basically one large boiler providing heat to all these houses, and everyone has a separate heat meter rather than everyone having separate boilers. So we'll talk a bit more about that later. And again, another set of houses might have some heat pumps installed, but obviously they'd have to be insulated very well and airtight. So you'd want your house to be hitting at least a B or C, if not more, in order to make a heat pump viable. Then as the community gets good at doing these some small and medium scale projects, then they might venture into community-owned wind farms. And again, this is just an example of a community or village on the coast. So obviously instead of onshore wind, you could have offshore wind farm, and the community can become part of these projects now through the new Renewable Electricity Support Scheme. Again, just an idea that wave generators will hopefully see this kind of technology being deployed over the next decade, and then also tidal generator. Okay, so SEAI released about 2 or 3 weeks ago their 2020 update, and it's actually data from 2018 because it takes so long to actually collate all of the data from all of the different sources and to evaluate it. So it's actually up to the end of 2018. This is how Ireland has performed up to the end of 2018 versus our 2020 targets. So our overall target, as we're a member of the EU, is to reach 11% renewable energy to reach 16% renewable energy by 2020, and up to the end of 2018, Ireland has reached 11% of that. So then we've split that energy target, that overall energy target, into transport energy, heat energy, and electricity. Okay, so within transport energy, we have a 10% target of all transport energy to be renewable by 2020, and we've only reached 7.2% of that. In heat, we have a target of 12% of all heat to be from renewable energy, so that's a 12% target again by 2020, and we've only hit 6.5% of that target. And then electricity, we have a 40% target for 2020, and we've reached just over 33% of that target, again up to the end of 2018. So as you can see, we're not on track as a country in meeting our renewable energy targets, and hopefully we can reverse that trend over the next decade. And in that, we have our new climate action plan in 2019. It's a good start. It doesn't solve all our problems. Obviously, it's just a document at the moment, but it does have some high-level targets there, something to achieve up to 2030. So in relation to heat energy, the climate action plan is targeting 600,000 heat pumps to be installed by 2030. 200,000 of those are going to be for new houses, and then 400,000 are going to be for the homes that are going to be retrofitted. Okay. Again, within the climate action plan, they're looking to deliver 2 new district heating systems. I'll talk a bit more about that towards the end of the presentation. And then obviously, you might be aware that SEAI now have the support scheme for renewable heat, which is supporting biomass and biogas technologies, either providing heat or heat and electricity. And again, I'll talk a little bit more about that now. So the support scheme for renewable heat, it's open to commercial, industrial, agricultural, district heating, public sector and other non-domestic heat users that aren't part of the European Emissions Trading Scheme. Entities that are part of the Emissions Trading Scheme, such as Dublin Airport and other large pharmaceuticals, large agri-dairy co-ops, they're part of the ETS sector, so they're not able to apply for the support scheme for renewable heat. But if you think about sort of your small or medium-sized businesses, such as hotels and that, they're able to apply for the support scheme for renewable heat. So it's something worth thinking about in your community. So the support scheme for renewable heat, it aims to bridge that gap between the installation and operating costs of renewable heating systems versus conventional fossil fuel alternatives. So obviously a lot of these non-domestic users, they have boilers, oil or gas boilers, and they might come to the end of their life after 15 or 20 years, and a decision has to be made to say, well, do we replace that now with the same technology and lock ourselves into that carbon intensive decision? Do we continue to burn oil or gas for the next 15, 20 years again, not knowing what the price is going to be? Or do we look at an alternative option, such as this support scheme for renewable heat, take the jump and take that support from SEAI and the supports that are available, and have a renewable heating system installed in our premises? So again, just broadly to outline at a very high level, the scheme is going to support 2 things. It's going to support an installation grant, which covers about 30% or up to 30% of the cost of an air, ground or water source heat pump. Okay. And then separately, it's going to support an ongoing operational support, a 15-year tariff based on usable heat output from either a biomass boiler or a biomass high efficiency combined heat and power unit. Okay, so this is where you can burn wood to generate electricity and then also generate heat. Okay, and then the ongoing operational support is also available for biogas, which is what I'm going to talk about later as well. This is produced through a process called anaerobic digestion, and you can have a biogas boiler or again a biogas high efficiency combined heat and power unit. Okay. So we'll link to more information on that later as well. And just to give you a quick look at the ongoing support tariff, just to give you an idea, you see there, the first column is the tier, so basically what size or the amount of heat consumption or heat demand that your premises might have. So in tier 1 there, if you have a demand of 0 up to 300 megawatt hours per year, and you are meeting that demand with a biomass heating system, you will get 5.66 cents per kilowatt hour produced. Okay, and then if your system is producing a little bit more than that, between 300 and 1,000 megawatt hours per year, then obviously the tariff is reducing a little bit, and so on and so forth. The tariff reduces the larger the system. And the column on the far right hand side is the cost you get per kilowatt hour of heat produced from an anaerobic digestion or biogas heating system. Okay, so I'll talk a bit more about what biomass and biogas heating systems are now. Again, there's some of the references just for the first few things I've talked about. So before we go into the detail of the different technologies, I'll just talk a bit about some of the basics of energy, how we measure it, the quantities used, and some of the principles. So when we talk about energy, we're talking about the conservation of energy, as in energy can neither be created nor destroyed. It can only be transformed or transferred from one form into another. Okay, but whenever we transform or transfer energy, some of that energy is lost into the system. To give an example of that, specifically in relation to an oil or gas boiler, on the left there you have your oil or your gas as a primary fuel, and that is chemical energy. So within that fuel, there is in fact 100% energy is embodied in that chemical energy. We introduce the oil into our boiler, and obviously it's transformed into heat through a combustion process. And as it combusts that chemical energy, we lose some of that heat. We lose about 10% of it in this example here. So straight away you've gone from 100% energy down to 90% energy. From the oil being combusted and transforming into heat, we then transfer that heat energy into the water heating system that we have in our homes, to run through our radiators and pumped through our radiators. And as we transfer it from the boiler into the actual heating system and our radiators, we might lose another 10%. So you can see there that anyone's boiler or heating system is about 80% efficient. Okay, this is just a high-level example. Okay, obviously some systems are more efficient than this. And again, just to give an example of in relation to electricity, for the efficiency of wind turbine. So you have your wind power on the left-hand side there. Again, wind power is the kinetic energy of the wind, and again, there's 100% energy within that. Now, the wind turbine can only actually capture a certain amount of that because it only has 3 blades. So straight away, you're only actually capturing about 55% of what's available. The energy has to then go from the turbine blades into the generator, the gears, and the generator, how it turns that motion into electricity. And again, there's some mechanical losses within that. So straight away, you're down to 45%. And then you also have losses when you look at power control. You have to take that electricity that you've generated on the wind farm. It's usually non-synchronous generation, so you can't just throw that onto the grid, because you would all be in trouble if that happens. So it has to be turned into a usable form of energy for the grid to be able to use it. And again, there are some losses in that. So you take maybe a 5 megawatt wind farm, and it's only actually producing maybe 2 megawatts of power when you factor in all of the efficiency of the entire system. Again, just a little bit about energy units and quantities. So we've work, energy, and power, and again, these terms are used interchangeably and can sometimes be confused with each other. So work is the provision of something useful, such as heat or light or motion. Energy, we need energy in order to do work, and we measure energy in kilowatt hours and megawatt hours. And you can see that on your electricity or your gas bill. Your oil bill is in litres, but there's ways to convert that to kilowatt hours, and you'll see that a little bit later. And then we have power. Power is the rate at which work is done, so it's obviously energy divided by time. And we measure the power of something in watts, kilowatts, and megawatts. So then just to give some average household energy usage. So the average house in Ireland might be a 3-bedroom semi-detached. So that house will use approximately 11,000 kilowatt hours of thermal energy. And then for electricity, it'll use just over 4,000 kilowatt hours of electricity. So it's interesting to note that you spend almost the same in heating and putting electricity into your house, yet you're actually using more thermal energy. And we see that here on the next table. Sorry, we'll see that again in another slide. And this is just a graph or pie chart to show where the energy is used. The majority is space heating, then water heating, then you have your lighting and appliances, and then some cooking. So again, you can see here the typical cost per kilowatt hour. So electricity in a domestic setting or in your home is approximately 17 cents per kilowatt hour. Then you have oil, which is about 7 cents per kilowatt hour, and then natural gas is even cheaper. It's less than 7 cents, about 6.5 cents per kilowatt hour. So you can see straight away per kilowatt hour, oil and gas are much cheaper. And then obviously on the right hand side we've got some commercial rates as well. Okay, so that was just to go through some of the basic principles around energy use and the terms that are used. So I'll talk about solar energy now. When we talk about solar energy, there's two things, actually there's more than two things. I won't go into all the details. There's solar PV electricity, and then there's solar thermal hot water. So today we're obviously going to talk about solar thermal hot water. There is another technology called concentrated solar power, and again that's a topic for another day, but it's very interesting, and there's been some of those installed in some very hot countries with very hot climates. But today we're going to focus on solar thermal hot water. There's different types of solar thermal hot water systems or solar panels. You might see flat plate panels installed on people's roofs, and more commonly now we're seeing the evacuated tube hot water systems, and these systems work just that little bit better in the Irish climate. So I'm just going to focus on these today because they're generally what people are installing now. The flat panels do work, they work quite well. The evacuated tube are just that little bit more efficient. So this is a cross section of the evacuated tube panel. So the evacuated tube absorbs solar energy and it converts it to usable heat. There's a vacuum between the two glass layers, and this insulates against heat loss. Obviously the tube collects those solar rays that are going into the tube, but then it's not allowed back out. So then the heat transfer fin, again that's shown here on the right hand side. This helps to transfer the heat to the heat pipe. Okay, so then the heat pipe is a copper vacuum pipe that transfers the heat from within the evacuated tube up to the manifold at the top of the solar panel. The manifold is an insulated box and it contains the contoured copperhead pipe with dry connect sockets. So this is how we capture the heat from the sun into the solar thermal panel. And you'll see now in the next slide how that gets transferred through the hot water system. So you see the sun's energy coming in there through the evacuated tube panel. In this case, it looks like a flat panel, but the principle is the same. It comes in, you have a pump control station. So you're taking that hot water out from the manifold of the solar panel, and you're bringing it into your hot water cylinder, which is you're giving some of the heat from your solar panel into the hot water cylinder. You're also getting some heat through your oil or gas boiler, and then you also might have an immersion involved. So you have three sources of heat there going into your hot water cylinder, and that's producing water into your domestic hot water system. Okay, so some of the considerations then when it comes to solar thermal. So a well-designed system can supply between 50 and 70% of your domestic annual hot water requirement. That's for the hot water in your taps and in your bath, and not in your radiators. Ideally, you're looking to have installed on a south-facing roof at between a 30 and 45 degree angle, and it costs about 800 to 1,300 euro per metre squared of collector area. And you would need about 6 metres squared for a 4 to 5 person household. So that system will cost you about 4,000 to 7,000 euro. And then the payback is generally about 8 years for a system such as this. And for that, SEAI will give you a grant of 1,200 euro towards that initial cost of 4,000 to 7,000 euro. You can see there it suits a regular daily hot water demand. Again, this is just a short case study about a dairy farm in Longford that installed a couple of solar thermal panels. And it's saving 1,300 euro per year since it's installed it. So you can learn more about that at the link there. So it's good to see some case studies of how these systems are working, not just in homes, but also in small businesses like this. So then heat pumps, there's been a lot of talk about heat pumps recently. When we talk about heat pumps, the two main ones that people generally talk about are air source heat pumps and ground source heat pumps. One is taking energy from the air, picture on the left, it's then taking the heat energy out of the air and then letting it out into the house. Again, the one on the right is taking the heat energy that's available in the ground, and again it's taking it in through the heat pump and then into the home. The question is often asked, is a heat pump renewable energy if it is in fact using electricity from the electricity grid, whereby we're using a large proportion of wind, in fairness, to generate electricity. But then also we have gas plants, we have peat plants, and we also have some coal plants that are providing electricity to the grid. So that's why the question gets asked, well, is it renewable if your electricity source is actually coming from a fossil fuel? But the answer is, in fact, yes, because it does use electricity, but it uses that electricity to collect mostly free environmental energy. So those free sources of energy are the air and the ground or water. And the way we measure the efficiency, it's not strictly the right term, but it's the term that most people use. And the way we measure the effectiveness, I suppose, of a heat pump is the coefficient of performance. So the coefficient of performance for a heat pump can be about 3 to 1, and some are up to 4.5 or 5 to 1. And in general terms, we say the coefficient of performance is about 4 to 1. So you can see here just a diagram on the right-hand side. You have a house, you have your electrical grid, so you have your electrical power in the green arrow there, 1 kilowatt hour coming in. So you're using that electrical power to take your heat from the environment, the blue arrow on the right hand side. So you can use that 1 kilowatt hour of electrical power to take the 3 kilowatts of heat from the environment. So then you're taking all that and you're actually providing 4 kilowatts of energy into your house. So this is why we say that it's in fact a renewable energy, and indeed why SEAI are grant funding them. So the basis of operation, how does a heat pump work? Often people say, oh sure, heat pump's just like a fridge in reverse, but then people might not necessarily know exactly how a fridge works. So I'll go into a little bit more detail. So the operation of a heat pump is on the basis of heat transfer, in that heat moves from something warm to something colder. So how do we get low environmental heat into our house? And this is just a typical example of a house. The house is at 12 degrees Celsius and the outside air temperature is at 6 degrees Celsius, and then your ground temperature might be at about 8 degrees Celsius. Okay, so obviously the heat from the house is getting taken away. It's moving from hot to cold unless we reverse the trend and put heat into our home. Okay. So a couple of fancy terms here. So a heat pump generally relies on these different cycles, compression, condensation, expansion and evaporation. And in order to manage those, you need a compressor, condenser, an expansion valve and an evaporator. Luckily all of these things are in your standard heat pump. And the real key thing to how these heat pumps are working well is down to the refrigerant that's used. That's the medium that's used, and that's what's circulated. It's what collects the heat and what gives off the heat on the other side of the heat loop. And you can see there, it works on the basis that it has a very low boiling point of minus 48 degrees Celsius. So that basically means if the outside air temperature or ground temperature is above minus 48 degrees C, then there is actually an ability to take heat from that source, upgrade that heat, and then give it into the house. Obviously your heat pump would have to work very hard at that temperature, but we don't often come up against that temperature in Ireland or indeed in Europe. So I'm going to talk about the evaporator on the left in blue, the blue arrow going upwards. So the evaporator picks up free environmental heat as it passes through the evaporator and it changes into a vapor. Then it moves into the compressor. The compressor is what uses the actual electrical energy to increase the pressure and therefore temperature of the refrigerant. Then it moves into the condenser. It releases heat to colder water in the heating system as it passes through the condenser, and it changes from that vapor back into a liquid. And then we have the pressure and temperature is reduced as it passes through the expansion valve. Okay, and then the cycle repeats itself. So you might have your refrigerant, again on the bottom left of the diagram there, you might have your refrigerant coming out at 3 degrees Celsius, it passes through the evaporator, which is outside of the house. You've then picked up some energy, so you're now at the point where it says primary circuit. you're now at the point where you've got from that 3 degrees Celsius up to 6 degrees, and you're going to further use the compressor to increase the amount of energy from that 3 to 6 degrees. You're going to also take some heat from your secondary circuit, that's some of the residual heat in your home, and then you're going to bring that back through the condenser, take the energy out, and it could be up to 40 degrees Celsius in order to provide some of your hot water requirement, and it'll also heat your home to a comfortable 20 degrees C. Okay, so that's just a very basic explanation of how a heat pump works. Okay, so some of the considerations then when we're talking about heat pumps. An example there on the diagram on the right is a ground source heat pump. So you obviously have to have space for the collectors, either in your garden, or it might not work well in a small urban setting. So some consideration has to be given, and obviously you can do it in two ways. You can have horizontal loops, which you need a wide area of land for, or else you can do a vertical pipe to go deeper into the ground to get a better source of heat. Again, these can be expensive things to install, but you can achieve higher COPs, your coefficient of performance, through this method. And then we have air source heat pumps, and this is just an idea of what some of them look like. Heat pumps have been around for a long time. You see them on the sides of buildings, especially industrial units and that, for refrigeration. And I suppose they're not all too different from what you see. They're now putting them on the outside of homes that have been retrofitted, and new homes as well. Again, they can be used to retrofit with your existing radiator system. So your existing heating system, your radiators and your pipes and the water, you can still use that with a heat pump. It can be upgraded. You don't have to completely change your entire heating system, but your home does have to be proper airtight and have a very good BER. So again, heat pumps are most efficient when they run at lower temperatures. So they don't work like your normal. You might come home some evening and say, oh God, the house is freezing. I'm just going to whack on the heating for an hour or two and be nice and warm then. And then sometimes your house might get too warm. So heat pumps don't work on that basis. They work on the basis of providing a nice, comfortable amount of heat throughout the day in a very efficient way. So again, as I mentioned, it works well if the home is well insulated, and if your house is airtight, or what we call if your drafts are minimised, and a fancy term for drafts is uncontrolled ventilation. So a cold house will take longer to warm up, so heat pumps work best in a controlled environment, providing lower temperature over longer periods. And again, this is SEAI's mantra to upgrade the fabric first, get your attic and your walls insulated first, before considering a heat pump. So again, you'll see a lot of the new houses being built in order to meet the building regulations that are around nowadays. Heat pumps are a good solution for that. So a retrofit in order to change out your gas or oil boiler, it might cost, depending on the size of your home, it might cost between 8 and 12 grand. And obviously a ventilation system will be required, what we call maybe a mechanically ventilated heat recovery system. The payback can be over 11 years, but it depends on a number of things. And in SEAI at the moment are offering grants of up to 3,500 if your home is pre-2011. And the way you figure out if your home is pre-2011 is the date that the ESB networks have assigned an MPRN number, meter point reference number, to the house. And then SEAI are also giving a €600 grant for air-to-air heat pumps. Okay, that's just a case study there that I won't dwell on. You can find out a bit more there in some of the links. But again, very large homes, 5 to 6 bedroom homes, and their annual energy cost for all of their energy demand is €1,200 there. So that's astounding, really, when you think about it, compared to a poorly insulated or old home, that's large. Okay, so just some ideas then, conscious that not everyone on the call is currently part of an SEC. You might only be starting out, you might not be fully aware of what the SEC program is. And the SEC program involves joining the network, getting a community charter together, doing your competency development, applying to SEAI for Energy Master Plan funding, and then carrying out an Energy Master Plan for your local community. And this slide here is just an example of what your community might decide to do as part of their Energy Master Plan activity. Energy Master Plan is EMP. So you could identify and rank your residential areas in your SEC. And I should say, obviously with that funding from SEAI, you're able to employ a contractor, an energy contractor or energy consultant to carry out your Energy Master Plan. So this could be something that your energy consultant could do for your community. So you could get them to identify and rank your key residential areas in your SEC. You could target newer houses between 2000 and 2010. And again, the reason why we're doing that is because they're the cheaper houses to upgrade in order to facilitate the install of a heat pump. You could also target areas with oil heating systems. And then next you could look at older houses which need a fabric upgrade to be suitable for a heat pump. Then step 2 of that is to raise awareness. You could host a local information event for homeowners and invite some heat pump suppliers and installers to present. You can find some SEAI registered contractors on the SEAI website that are operating in your area. And again, this is just the example of how you're linking some of the core competencies together in order to develop a project idea or a proposal for your community. And again, there's the links to most of what we've discussed. Okay, so biomass, biomass and biogas, and a little bit on district heating to get through. So biomass is after taking a bit of a pounding in that recent Planet of Humans documentary or film that came out recently, directed by Michael Moore. It's worth a watch, but don't be fooled by it completely. It takes a very narrow view of renewable energy. But it does point out some problems with biomass in that it has to be sourced sustainably. So I'll just go through what biomass technology is now at the moment anyway. So obviously some of the considerations for biomass, your site specifics, you have to have a good area to store your wood fuels, which could be logs or chips or pellets. And then obviously your boiler has to be close to that fuel store because it has to constantly feed the wood fuel into your boiler. And then your supplier of fuel, you're looking for fuel that is about 30% moisture content. Ideally, you want 25% moisture content, but 30% will do. If you're not achieving 30% moisture content, you're going to run into problems with your biomass boiler. Okay, so this is just an image of what a biomass boiler looks like. They're pretty much identical to how an oil or gas boiler works. You're feeding a fuel into a chamber, you're combusting it and transferring that combusted heat into generally a water source, sometimes an air source, in order to provide heat to your home or your building. That's just a note on gasification. It's another way of extracting energy from biomass. I won't go into too much detail. And then also you can have biomass for CHP, which is combined heat and power. So instead of just using biomass to produce heat, you can use it to produce heat and electricity. So you could use the heat on your own site, and then you could possibly give or sell the electricity to a site close to you. Okay, so just to talk through some of the economics of biomass. So the capital cost based on system size, so obviously it's reliant on what supplier quotations you're getting. The savings are related to the cost of what you're already spending on energy and your fuel and energy. So this is what you have to take into consideration. So at the moment, or not at the moment because oil is very cheap at the moment, but in general terms, kerosene for your heating oil costs about 6 cents per kilowatt hour. LPG bulk, if you're in a commercial or industrial building, it's about 7 cents per kilowatt hour. So then you can see there the clear drop wood chips are about 4 cents per kilowatt hour. Okay. And then wood pellets are 6 cents per kilowatt hour. So on some recent projects that my colleague Mel has looked at, there's been payback of between 5 and 12 years. And this varies based on the upfront capital costs, the fuel costs that have been secured, and the length of term for that fuel supply contract, the actual heating demand of the building, and in your operation and maintenance cost and your O&M contract that you might have. So again, just to talk about some of the key points, maintenance is very important. Your ash removal, your feed auger servicing. This is how you're actually taking your wood fuel from your where it's been stored, taking it into your biomass combustion chamber, and then again your combustion chamber cleaning. So these are just three of the things you have to keep an eye out for. And again, most of the bad stories you hear about biomass, either in the domestic setting or non-domestic setting, they're down to mechanical failure. It's been installed, possibly not commissioned well, and it hasn't been maintained properly. You might be burning fuel that's too wet. So so a lot of these things can in fact be avoided if it's set up correctly in the first place. And then some of the options are to have your own trained or skilled maintenance personnel. Again, as we talked about, a robust operation and maintenance contract. Get your supplier to include this in the analysis. So you might get the installer to include for a 5-year contract to install and maintain the system. And then obviously you have an option of retaining your existing system as backup. And then this is just an idea about the types of local energy supply contracts that I suppose the market would like to see. And it's helping more so large businesses make that jump from their fossil fuel heating system to this kind of system. So you'll have these local energy supply contracts, and they can work at different stages of the value chain. So you see there the value chain is made up of, starting from the left, your finance and the specification and design of your system, actually building or installing that system, where are you getting your fuel from, what's the quality of that fuel, as we discussed, the operation and maintenance of your system, then obviously selling the output through the new support scheme for renewable heat that I talked about at the start. So you can see different companies will offer different parts of that value chain. Okay. Again, there's another case study. I won't dwell on that because I have a few more slides to get through. But there's a link there on that slide, and the slides are going to be shared with everyone, so you can go through that case study in your own time. And again, just some energy master plan activity that you can do if you or your community are interested in looking at biomass energy. There's a couple of points here that you can talk to your energy consultant about and talk to your different businesses or non-domestic users in your town or city or village. Okay, so biogas. So biogas is generated through a process called anaerobic digestion. So that's digestion in the absence of oxygen. Aerobic is oxygen, anaerobic is without oxygen. And this is what your typical AD plant looks like. Again, we often say, what is foundation level knowledge for AD? Every time I talk about AD with someone, I learn something I didn't know or unlearn something that I thought I knew. So it's a very scientific process. And just to give you an idea of that, on the right hand side, I won't go through all of this in detail, but you have all these different chemical processes going on in order to digest your substrate and turn that into your fertilizer and your biogas and the other outputs that are there. Okay. So you've chemical processes called hydrolysis, acidogenesis, acetogenesis, and methanogenesis. Okay, so it can be quite complicated. So it's important to point out, though, that anaerobic digestion, it was actually originally developed to treat waste, because the treatment of waste is a huge cost for an agricultural business or for a farmer even. They have to treat their waste in accordance with EU regulations. So AD came about because of this, to say, well, this is costing us a fortune. Why don't we try and treat this waste on our own land? And actually the byproduct of treating the waste is energy. So again, in its simplest description, anaerobic digestion is a sequence of processes by which microorganisms break down biodegradable material in the absence of oxygen. So AD provides waste treatment, because it digests the waste to a more stable material, and I'll talk about the different types of waste in a moment. It provides biogas, which is methane and CO2 as a byproduct of the digestion, and then obviously fertilizer as it's digested from the process, which is a useful waste product to be left with. So again, here just an image. So your feedstock or substrates or the waste. So you could have food waste, you can have industrial waste, you can have slurries, and farmyard manure. So you can see there in the yellow circles, they're all your substrates or your wastes or your feedstocks. They're going into your anaerobic digester. In brown, you have your digestate. This is what's left over after the process has run through. You have your biogas coming off in dark blue there, and then you can choose to what you want to do with that biogas. You can either put it into a boiler on site locally or as part of a district heating system and generate some heat. Or in fact, you can put it into a CHP unit, a combined heat and power unit, and you can generate heat and electricity. Okay, so it's a very, it's just like natural gas. It has to be upgraded to the quality of natural gas, but it's a very useful form of energy. And again, this is just an idea of a case study and to give you an idea of what the different components of an AD system look like. So this plant here in Northern Ireland is for 300 dairy cattle. So obviously the plant works off that slurry feedstock, and it powers the biogas that comes off. It powers a 90 kilowatt gas boiler and 100 kilowatt CHP, which produces 100 kilowatts of heat and 23 kilowatts of electricity. And you can see there just an idea of what a district heating system might look like. It's a fairly basic concept. You're not just heating one building, you're heating a couple of buildings, and you're piping that heat in between the buildings. Again, this just gives you an idea of the actual value, and again, in your own time, you can go through this in detail. But starting at the top there, you have your dairy cow slurry, 1 ton, goes through your digester, and then you're producing biofertilizer. And that amount, that ton of cow slurry is turned into those amounts of biofertilizer on the bottom left to the value of £5.42. And again, you're taking your digester, you're generating biogas, and the electricity that you can use once you've taken away the electricity you're using on site is about £6.6 per kilowatt hour of electricity. And then again, your heat, there's a value to the heat as well. So you can see there from a ton of cow slurry, you have a total value of £12.57 for your fertilizer, your electricity, and your heat. Okay. And again, then another case study, something closer to home in County Limerick, green gas AD plant. They've actually turned that into a high efficiency combined heat and power plant. So we'd like to see more of these things, and it definitely is a way for agriculture to take part in the climate transition. And again, some energy master plan activity there that you can do if you or your community are interested in biogas or anaerobic digestion. Okay, so I just have 2 or 3 slides left to go, and then I'll pass you over to Mel. So just a quick update on district heating. District heating has been used for years and years, decades across Europe. It's kind of associated with Eastern Europe, but it's used very well also in Austria and that. So what is a district heating system? It's a thermal energy network that distributes hot water through insulated supply and return pipes, and it can serve commercial, residential, institutional and industrial energy needs for space heating, hot water, space cooling and industrial purposes. So you can see on the right hand side there, this the unit with the yellow roof on it might be a data center, or it might be a waste incinerator, and it's producing excess heat. So it can provide that heat to some small businesses, some homes, some apartments, to a hospital, and also to some other smaller medium business users. So the advantages are you have much higher energy efficiencies. Instead of everyone installing separate boilers, you have one big boiler producing heat for everyone. You've reduced consumption of energy resources, obviously capital cost savings, and then reduced operating and maintenance cost for your commercial and residential customers. So what's happening closer to home? You have the Dublin district heating system, which has been allocated funding about a year and a half ago, 20 million for the Dublin district heating scheme through the Climate Action Fund. That project is currently at validation stage, and Dublin City Council are liaising with the Danish district heating advisors. Codima, Dublin's energy agency, is also involved, and the National Development Finance Agency. So there's some more detail there at the link I've provided at the top. And this is just an image. So what we're talking about here on the top left of this image is using the waste incinerator at Poolbeg, using the waste heat from that and supplying it into a district heating system into these pipes that will be piped into different buildings in the docklands around Dublin. And again, then a similar scheme, albeit a little bit smaller, is the Tala district heating scheme. Again, through this Climate Action Fund, it's after securing 4.5 million for this district heating scheme, and this is being run by South Dublin City Council, SDCC, and we're talking about using waste heat from Amazon data centre. You can see that in the map here, the energy centre. Sorry, the pink building at the top is the Amazon data centre. So that's going to have data centres use a huge amount of, they require a huge amount of cooling energy. And so you're trying to take the heat from all the servers, and so they're going to be able to take that heat, put it into this district heating system and supply these different buildings in and around Tala with cheaper, cleaner energy. And again, it's just a good example of a collaboration between a county council and energy agencies such as Codima, and then an EU research program, and it shows what's possible when different entities act together for these climate action projects. Okay, so that's it from me. I will pass you over to Mel to briefly go through. Mel, you giving us the story about heat or fire this time?
It's not about virus. No. Okay, so Stevie, if you mute yourself, we won't get the feedback.
Sorry.
Okay.
Got a slight echo from you there, Mel.
Is that better? I think Stevie's muted now, so.
Oh, yeah.
Okay. Can everyone see my screen there? Good intentions, poor outcomes?
Yep. See that fine? Yep.
Okay. Okay, so this story, it was initially intended for yesterday's webinar, which was around community engagement. So it's a story about as an example of the importance of knowing or understanding the community that you're working with. But in any case, it actually fits okay with today's webinar, as it starts with the Northern Ireland Renewable Heat Incentive. Now, we've all heard about this. It made a lot of headlines, but initially it was intended to provide an incentive to using wood fuels instead of oil and gas. And of course it did work, but then the system, the scheme itself didn't have enough controls or limits, or it didn't have proper controls or limits, and everybody began to burn wood fuels even when they didn't need it. And our lovely tabloid press came up with the headline, Cash for Ash, and images like this. And it even spawned a book by Sam McBride, and poor old Arlene Foster became the poster figure for this, and I'm pretty sure that she wasn't at all as pleased with the whole affair as that book cover suggests. So we go from here, from this example of good intentions and poor outcomes, to another example by British administration. Now, I'm not picking on the Brits here. It's just that there are a lot of administrations made similar mistakes. It's just that this particular story lends itself to my story. So this all occurred during the British colonial rule of India. Although Britain was involved in India with trade and exploration centuries ago, the colonial rule, or the Raj as it was called, lasted from sometime in the middle of the 19th century to about the middle of the 20th century. And in Delhi, they had a lot of these fellas, the Cobra. So this, obviously, India is a natural environment for snakes. Delhi had a huge human population, which means a lot of food, a lot of waste, a lot of insects, and a lot of rats and other things. That this makes it perfect for the cobras. So the cobras flourished here. Now, as it happens, the Indians were used to this. Okay, so every now and then somebody got a bite, and every now and then somebody died from those bites. But for the British authorities, many of whom had maybe arrived there just wanting a sunny version of London, this particular animal here was a most un-British vermin. So the governor of India decided to provide an incentive to the community to get rid of the cobra, and they offered a cobra bounty, which was a bounty for every dead cobra turned into a police station. And as it happens, so the Indians were fine with this. It was a handy little income stream, a nice little earner, and they went out and started killing the wild cobras, and of course bringing them into the police station and getting their cash. And it was great. It worked for everybody. There are some anecdotes where some of the Indians realized they could take advantage of some newer police recruits who had just arrived from Britain, and they would bring in a cobra skin. And of course, the poor young lad in the police station would offer out the bounty, not realizing and not having learned yet that cobras actually shed their skin. So that was the start of the abuse of the scheme. And beyond that, then the Indians said, why am I chasing cobras down the street when I can simply get myself a mammy snake and a daddy snake, put them in the backyard or in the spare room, put on some Barry White, make sure they've no access to contraceptives, and let nature take its course. And then they had this huge, plentiful supply of farmed cobras that they could kill and bring in for the bounty. So this started to happen, and nobody was killing the wild cobras, and the wild cobra population spiked. And eventually, the British authorities got wise to this, and somebody probably got sacked, and then they cut the bounty. So the Indians, with all these farmed snakes in the backyards and their spare rooms, said, "There's no point keeping these lads here anymore," and they let them off into Delhi. And it was the largest infestation of cobras that they'd ever had in the city. So this actually gave rise to the term, the Cobra Effect, which essentially it's a law of unintended consequences from good intentions. Now, if I'd say a lot of our modern day journalists, particularly after the Cash for Ash scheme, would love to get a time machine, travel back to India at that time, and come up with the headline, Cash for Asps. So that's the end of my story today.
Brilliant, great. Thanks to both Stevie and Mel for that. Now we've had a good few questions coming in during that. So I know we're basically right on 12 o'clock now. So if anyone does need to dash off, that's absolutely fine. And if anyone wants to hang on a bit for the bit of a Q&A, that's fine too. So I'll just scroll back up to where we had our first one. So John was asking, does the payback for solar thermal include the reduction in cost due to the SEAI grant? So just to mention something on that from my side, the solar thermal grant available through SEAI is the total value of that grant is €1,200. And I think that the typical cost really of a solar thermal system would kind of be between 800 and 1,300 per square meter. So I mean, the cost of the system would have a significant effect on the payback period. So what we do recommend people do is when they are looking to input a solar thermal system, that they go out and get a number of different quotes from installers so that they can get, kind of a variety of prices, because it's important to consider a number of options like the price, the payback period, and, the service agreement with the chosen supplier. So getting proof on the payback period when you go out to get your quotes would be something that we would recommend, because whatever the inevitable cost of the system is will have an impact on the payback period. Does anyone else want to jump in on that at all?
Just that we would normally advise on this, and solar thermal is probably one of the hardest ones to quantify in terms of the benefits as to how much it saves you. what we normally advise is that if you are using hot water, on a daily basis, on a regular basis, then this is then it's worth doing, and then the payback will at least be within the life of the system, and the grant will obviously reduce that payback.
Yeah.
If you're not there using that hot water, then you're just not getting the benefit of it. And again, as Caoimhe had said, when you're getting a proposal from an installer, ask them for a breakdown of the typical solar output and the typical saving you're going to get throughout the year. And obviously it'll vary throughout the year. You'll get more in the summer than you will in the winter. But that's the best thing to do is to get that feedback. And just bear in mind as well, it saves hot water that you're normally heating with oil or gas. Appliances like washing machines and dishwashers, they only take a cold feed, so you're not saving that hot water. Those modern appliances, they take a cold feed and they heat it up themselves using electricity.
Yeah, great, thanks, Mel. Next one there, is water being used as a source for heat pumps in Ireland?
Yeah, so I had offered some answers on this. Yes, the answer is yes. So water is a pretty good source. Anything in the ground in Ireland is essentially likely to be a water source as well, because you only have to dig a meter or so to get to groundwater in many locations. Water is a good source, and one of the questions there was around using canals, and I think I forget who asked the question, but they had pointed out that there would be issues there around working with the OPW and the canals. One of the technical challenges with using water when you put a collector into it is maintenance. So over time, you're going to get some scaling, some buildup of material on the collector, and that reduces the heat transfer efficiency of that. So you'd have to be able to clean it reasonably regular, depending on how clean the water was. So those are issues around that. Your ground source water or ground source heat pumps for homes, the deep version is in a borehole, and so that is essentially a groundwater source.
Yeah. Great, thanks. Yeah, and I can see, Mel, thanks. You've gone back on a couple of the queries there, which is really helpful. I think this one you may have gone back on. Is there much evidence in Ireland of the actual COPs of heat pumps when retrofitted into existing homes? A COP of 4 seems extremely ambitious in practice when you consider retrofitted examples and how these are used with existing homes, example radiators and behaviours. So I think, yeah, you had gone back on that, Mel. Just trying to find it down here. Yeah,
it's generally rather than just a COP, the term that most manufacturers have on their units and products now is a seasonal coefficient of performance, or SCOP. Yeah. That should be an indication of the average COP throughout the year. Obviously, it's higher in the summer, it's lower in the winter. The question is quite a good question around retrofitting. Is that representative in retrofitting? It does depend on how well the retrofitting is done, and that did bring up another question, I think, in the comments there, which is around radiators.
Yeah,
we say in here that you can use your existing heating system. What we mean is that you're unlikely to have to change the whole thing, and in some cases you won't have to change RADs or at all. It will depend on the overall heat loss coefficient of your home.
Yeah, so exactly.
If your home tends to lose heat relatively quickly, what you need is a heat distributor that provides heat to match that loss. So that may mean that you need a larger RAD or a larger volume, a larger volume radiator. It's the same reason why in a new build you would use underfloor heating, because you have lower temperature but a larger dispersal area or a larger emitter. So it's not a simple question to answer.
Yeah.
In terms of changing radiators, some experts will say to use an aluminium radiator, and generally you may get away with the same size radiator as your steel, because aluminium releases heat quicker. And then others suggest you need a larger steel radiator. Now, if you go for a larger steel radiator, there are two options. You can go for a bigger area one, so it's kind of changing from a 4 foot to a 6 foot, or you can go for a deeper one. The advantage of going for a deeper one, which is changing from a single to a double or a double to a treble, the advantage of doing that is that you're less likely to have to move pipework.
Yeah. Yeah, and yeah, I saw that question a bit further down, and obviously mentioning that the home is partially insulated as well, and like you said, Mel, it is all about that, the heat loss indicator and making sure that a dwelling's fabric or the heat loss is lowered as much as possible so that the heat pump can perform as efficiently as possible. And I have seen mention of potentially having to change radiators in homes so that the heat pump can kind of sync up with the system a bit more efficiently. But we do have quite a useful presentation that the team that work on the home energy grants have provided us with, which we can always share with people when we send out the slides for this presentation as well, because there's some really useful bits of information in there around heat pumps specifically, and the various different kind of measures that might need to be taken into account when looking to install a heat pump. So if anyone would like that, we can send it on, no problem, with the slides for this webinar as well.
Yeah, Caoimhe, I think your homeowner's guide to the heat pump is actually quite good as well.
Yes, exactly. Yeah, and that should be up on the website. There should be a link to that, which we can include as well. So that's grand. Right, where was I in the questions? Studies in the UK and Ireland show that typical air source heat pumps achieve COP of 1.5 to 3.5 in real world applications rather than 4. What measures can ensure efficiency in this higher range? So we've kind of talked about that there.
I think maybe the other measure to mention there is learning and training for the home owner itself as to how these things operate, how they should operate.
Yeah, so, that's very true. Yeah.
There are bad news stories of having had a retrofit and a good plumber comes in, installs it, and maybe runs through the controls, but that isn't enough to perhaps show the homeowner if there's a display there, if it's displaying a figure, what that figure means. Is it good or is it bad, or is it where it should be? So training is important and understanding of it.
Yeah, definitely. Yeah. Can a district heating heat pump system get hot water to every apartment in a 4-floor apartment block? Example, if a very warm car park is used as a source.
You would have to look at what the output of the car park heat is.
Yeah.
It's not clear what the source of the heat is in the car park. But yeah, you would just have to measure what's your demand for all of those apartments, and install the right amount of sufficiently powered pumps in order to get the heat up to the top floor apartments, if everyone's going to have a shower or bath at the same time. So you just have to do an analysis of what your output is. You might have to upgrade that heat. You could have a system whereby you're taking your waste heat and then you're just upgrading it at a central location, in order to provide everyone with the right amount of heat.
Mm-hmm.
Yeah, I think it's Alistair with this question again. Yeah, technically this is possible. You'd have to do the design and then the costings to see whether it's worth it or not. I know you're saying there, Alistair, that you think it's 21 degrees in the car park at all times. I would find that surprising. A lot of car parks that are shaded and underneath buildings, particularly below ground, tend to be quite cool even in the summertime. But if there's a lot of car movement, yeah, I can see, with exhaust fumes and things like that, you may have a lot of waste heat there. It's because of the shopping centre below. Okay, so there's heat rising from the shopping centre below. Okay, yeah, so that could work, and that means that it's not underground. Yeah.
Okay, great. I think the next few we've kind of gone through, and Mel's answered a few of them back. There's one there then. Is there a substantial risk in district heating using waste heat from data centres, i.e. the level of investment means there has to be certainty of supply of waste heat for decades, but commercial decisions by companies like Amazon, Google surely mean this may not be reliable?
Yeah, that's a fair point. How long are Amazon going to be there? Will they move on to the next tax haven when the time comes? But I suppose the point is that the system is in place, the district heating system is in place, and really then it becomes easier to figure out a source of heat. If it's not going to be Amazon, then you might look at another way of providing that heat in a renewable form. Obviously, it's a bit more complicated because there's just a lovely waste heat form there now existing, but the actual infrastructure is in place for everyone. But again, that would have to come down to how long are Amazon going to be signed up for, what's their lease. But there are risks in that, absolutely. There are risks.
You know, ideally we'd try and deal with that with a contract. So Amazon would have a contract to be part of this, because they wouldn't be doing this for free. It would be of some value to them. Mm-hmm. So it's a good point, and it's something we should probably bear in mind. The option there for a contract solution would be to have Amazon have a penalty, a buyout penalty, for ending before an agreed term that would cover the cost of installing perhaps a biomass system to feed that district heating system.
Mm-hmm. Yeah, great. Okay, thanks. There's one more then that came in. Are there bespoke solutions for farms? For example, a dairy farm with a large adjoining house. Is a conjoined system appropriate, and what might this be? For example, could a heat pump work for both?
Yes, there are some case studies on this. I hope I'm saying your name right, Suantri. If you email me, gavin.mel@itsligo.ie, I can share some case studies that I've got on this from another project.
Great, thanks, Mel. Okay, well, thanks to everyone for hanging on for the Q&A. Does anyone have any other questions before we finish up, or is everyone all right? I'll give it a minute there see if anyone's typing.
Just the address is there.
Oh, brilliant! Thanks, Stevie.
That's the address.
Okay, I don't see anything else coming in there. All good, thanks. Okay, well, if everyone is happy enough, then we can leave it there. And just to say a big thanks again to Stevie and to Mel for their contributions, and to all of you for joining today and hanging on a bit past 12 there for the Q&A. I hope it was useful, and we will send on the slides afterwards and some of the other bits and pieces that we chatted about there in terms of the heat pumps and some other useful bits of information for you. Okay.
Thank you.
Great. Thanks, everybody.
Thanks, everyone, for joining. Thank you. Take care.
Thanks. Bye-bye.